Hello everyone, in this class I am going to explain how to implement serial in parallel out left shift register in VHDL language by using Xilinx software. As we have discussed in the previous class that in case of serial in parallel out left shift register, we get the output from each flip-flops after a clock event, and the clock event can be edge triggered or level triggered. In case of edge triggered, it can be positive edge triggered or negative edge triggered. In our example, we are going to consider positive edge triggered events. Now, in this example, we are going to implement 8-bit serial in parallel out left shift register, and for that purpose here we are going to consider a 8-bit input sequence which is 00, 00, 10 and 10. So initially when there is no input fed into that register, in that case the initial output of all the flip-flops are unknown to us, and that is why we have used here U symbol. And when there is the first clock event, and in that case the first input which is 0, it will fade into the last flip-flop, because here we are going to use left shift register. So from left direction we are going to feed input one by one. So here D0, the last flip-flop, is going to receive the input which is 0 in here. So here the output of 0th flip-flop will be 0, and rest of the flip-flops will have the output unknown. Now after the second clock cycle, the second input 1 will be fed into the last flip-flop, that means the D flip-flop 0, and corresponding Q0 will have the value 1, and Q1 will receive the previous value of Q0 which is 0. Now similarly in the third clock cycle, the third input 0 will fade into the last flip-flop Q0, D0, and output will be Q0 which is 0. Q1 will receive the previous output of Q0 which is 1, and Q2 is going to receive the previous output of Q1 which is 0. Similarly, in the fourth flip-flop, the input 0 will fade into the D0 flip-flop. In case of fifth clock cycle, the input 0 will be fed into the D0 flip-flop, and in case of sixth clock cycle, the 0 input will fade into the D0 flip-flop. In case of seventh clock cycle, the seventh input which is 0, it will fade into the D0 flip-flop, and consequently the other flip-flop is going to receive the previous value of the previous flip-flop. And finally in the 8th clock cycle, the last input which is 0, it will fade into the D0 flip-flop, and Q1, Q2, Q3, Q4, Q5, Q6 and Q7 are going to receive the previous value of those flip-flops. And finally after the 8 clock pulse, we will have the input stored in our register which is 00, 00, 10, 10. Now let us try to implement that in Xilinx software. So open the Xilinx software, and after that click on the new source. Suppose in this example we are going to use serial in parallel out register, so name it like that, serial in parallel out register. After that create new source, select the VHDL module, so SIPO and R, so it will be a serial in parallel out register. Now the first input in case of serial in parallel out register is the clock, so CLK is the input, and another input is serial in, SIN, serial in input, as we can see. And the other output will be, if we are going to implement 8-bit register, so there will be 8 outputs after each clock event. So output, let us consider P out, and P out will have 8 values. So out, and MSB will be 7, LSB will be 0. And for SIN also, let us consider capital value for S, so SIN. Now click next, finish. Let me zoom it, the code segment. And within the architecture begin and construct, we are going to write down our logic. Now as we can see in here that all the flip-flops are going to pass the value to the next flip-flop with the help of some internal wires. So in case of Xilinx language, we are going to represent those wires with the help of signal. So as there are 8 flip-flops in this register, so there will be 8 wires. So we are going to use those 8 wires in our program to store the intermediary values or transfer the intermediary values, and that is why we need to have some signal. So signal, let us name it temporary signal, and the type of the signal will be standard logic vector 7 down to 0 because it is going to store 8 values. Now after that we are going to write down our logic within the process. So we are going to create a process and within which we are going to write our logic. So let me create a process, and process is going to receive the input clock, and after that it is the begin and end of the process, and within process we are going to write down our logic. And our logic is very simple, that first we need to check whether there is any positive edge clock or not. So we need to check whether clock having a value 1 or not. Simultaneously there should be some clock event, and if this scenario occurs then we are going to proceed further. And proceed further is similar. So basically D0, or that means the first wire which is temp0 is going to receive the input from serial in, and similarly the temp1 is going to receive the value of temp0, temp2 is going to receive the value of temp1, and temp3 is going to receive the value of temp2, and this is how things should work. So temp is going to have the value temp6 down to 0, and after that we are concatenate the serial in. So this is our logic. So what ampersand is doing here in Xilinx ampersand is used for concatenation. So suppose earlier value of temp was something like this. Earlier value of temp is suppose 00000000, and SIN value is suppose 1. So after this operation the temp is going to receive the last 7 values of temp, and after that it is going to concatenate the value of SIN which is 1. So this will be the updated value of temp. As we can see in here, in each iteration we are going to feed one value in the last position. So we are shifting to the left direction 1 unit. This is how things are working in case of SIPO left shift register. Now let us close this if construct, and when it is done for all the 8 bits of the register, we need to put the final value in the actual output. Actual output in our example is P out. So P out is going to receive the value of the temp, and after that put a semicolon, and this is how our logic segment is done. Save it, and after that compile it. As you can see, compilation is successful. So let us go to the behavioral section and create a test module to test this logical segment of 8-bit SIPO register. So create a new source, create test bench waveform, let me name it testing, and after that click next. And here I am going to show you another trick in this example, that suppose until now we have seen that simulation window size is 1000. Now I want to increase the simulation window size or test bench waveform size from 1000 nanosecond to 2000 nanosecond. So finish, make it 2000 nanosecond. So You can see from 0 to 2000 nanosecond you can feed the value in this test bench waveform. And in our example we have considered the example 0 0 0 0 1 0 1 0. So how these inputs will be fed into the 8-bit left shift register? Initially the 0 will be fed into the register, and after that 1, after that 0, then 1, then 0 0 0 0. This is how the input will be fed into the SIPO left shift register. So according we need to put the value in the test bench waveform. So initially the SIN value will be 0, then it will be 1, again it will be 0, then it will be 1, and finally all the 4 values will be 0. So it is 0 1 0 1 0 0 0 0. This is how the input is going to be fed into the SIPO left shift register. So now save it, and after that we need to use another trick which I am going to explain here. Select the testing module, and after that go to the simulator and right click over it, go to the properties, and in the properties go down and select the run for specified time. Now as the test bench waveform length is for 2000 nanosecond, we need to make our simulation window size also 2000 nanosecond. Now apply and then click OK. After that let us simulate our VHDL module with the help of this 2000 length test bench. So as you can see, this is our simulation window. So as you can see, initially in the first clock the serial in is 0 and clock is 0, and that is why the P out, the last flip-flop of the register, will have the value 0. Initially all the flip-flop status is unknown to us, and after the first positive edge clock, the last flip-flop, which is D0, is going to receive the value of SIN, serial in, which is 0, and that is why it is having a value 0. Similarly, after the second clock, you can see the P out, which is the last flip-flop, D0 is going to receive the value serial in 1, and the previous value of D0 is going to be received by the next flip-flop D1, which is 0. Similarly, after the third clock cycle, serial in is 0, and that is why the P out is 0, and P out 1 is receiving the previous value of P out 0, which is 1, and P out 2 is going to receive the previous value of P out 1, which is 0. Similarly, after the fourth clock cycle, the serial in is 1, and that is why the P out is 0. P1 is receiving the previous value of P0, P out 0, which is 0. P out 2 is receiving the previous value of P out 1, which is 1, and P out 3 is receiving the previous value of P out 2, which is 0. Similarly, after the fifth clock cycle, you can see the values is 0 1 0 1 0. After the sixth clock cycle, the value is 0 0 1 0 1 0. After the seventh clock cycle, it is 0 0 1 0 1 0. And after the 8th clock cycle, okay, after the 7th clock cycle, this will be the value 0 0 0 1 0 1 0, and after the 8th clock cycle we will have the value 0 0 1 0 0 1 0 1 0. So as you can see in this example, after the 8th clock cycle we will have the value 0 0 0 0 1 0 1 0. This is how the value is going to store in the register. So here also after the 8th clock cycle we are going to have this value, which is 0 1 0 1 0 1 0 0 0 0 from the MSB to the LSB. So that is how you can implement serial in, parallel out, left shift register. Thank you.